Okay, guys. Okay, so guys, so your last cosmology lecture. I'm sure some of you are pretty happy. Oh, you have Matthias, but who knows what he's going to talk about, right? So, okay, so today I want to connect back to things that Scott and Neelima did, and no more Boltzmann equations. Well, maybe just one. We'll just basically look at some numbers and try to basically walk our way through why the CMB in large-scale structure are such good evidence for dark matter. And one thing that you haven't heard too much about, we'll just do a little bit of it, BBN, and how that plays into the whole story. Okay, so that's the plan for the first half an hour or so. Okay, so I'll start with something that Scott wrote down, which is the scale at equality. So he mentioned that this is something that we can now measure really well, for example, from the power spectrum. And so you guys saw this plot of P of K versus K for the dark matter. And there's one scale in this plot, the way I've drawn it, and that's K eq. But there's also fluctuations on top of this, right? This is the baryon acoustic oscillations. The physics for that is essentially the same as the physics that goes into the CMB, and we'll talk about that next. But for now, we have this one scale that essentially determines what the power spectrum is. And so we can sort of take this, and I thought what I would do is I would take this and then combine this with BBN, and then we can sort of see how this evidence for non-baryonic dark matter comes out from this. Okay, so the idea is to take this and add BBN on top of it. Okay, so this K eq we can write out in different ways, but this is another way of writing this out is so I've taken out this 100 kilometers per second per megaparsec. So typically H naught is written like that, and so all I've done is taken that out. And this is just to tell you that this K eq is directly related to the scale factor or the size of the universe's equality, measured with respect to the size today. So in units where A is 1, so K equality is essentially telling you something about by how much the universe is expanded, or vice versa. Right? Now, omega radiation is something that we know reasonably well, modulo how many light degrees of freedom other than neutrinos there may be. So this omega radiation is times h square can be written out and I wanted to write this out so it's very clear what this N effective term is that we often use in cosmology. Okay, so this is basically the first part is the density in the photons, which since we know its temperature and we know it's a black body, we know really, really well. The second bit is the 411 to the 1/3 is that famous factor for the neutrino temperature. 7/8 comes from the statistics. 3 plus N effective. So the Z effective is just any relativistic degrees of freedom, but we're trying to quantify that in terms of how many equivalent neutrinos it would constitute. Okay, so you want to think of N effective as, sometimes people write this as N nu, but I think it's better to just leave it as delta N effective and just think of that as extra radiation. Okay, so if delta N effective is 0, we can write this out. We can. So this is 7.1 times 10 to the minus 5. Let me write it out here. Okay, and of course it depends on this. Okay, so we know this stuff, we know this very well, so you can plug that in there. A equality, remember, was defined as omega radiation over omega matter. Everything that moves is matter, baryons, dark matter, whatever it is, goes in here. So everything that's pressureless, and this is everything with equation of state close to 1/3. We can put h squares in there because those are the quantities that are better measured. Okay, and so essentially, if you know omega matter h square, we have everything we need to compute k eq. So you can put those numbers in, or use k eq, the measured value of k eq, and get out omega matter h squared. Doesn't really matter how we do it, but this for the latest Planck results is something like, I may be off here, maybe it's 4.2 or something like that, but it's somewhere around 0.14. And so if you plug this in, you're going to get k eq is 0.008 megaparsec. I think this is what Scott wrote down in last lecture also, right? So it's a scale, if you do 1 over k eq, it's a scale roughly of order 100 megaparsec. Okay, that's where that transition is. So it's the scale that enters the horizon at matter radiation equality. It basically controls the linear power spectrum features. Okay, you can measure this and back that out from large scale structure measurements. You can do that from CMB. And so now we're left with this question. Okay, so we have omega matter h squared. That's all of the matter. How do we get the baryons? And there's a couple of ways to go about it. You can use clusters. Clusters tend to be systems that if you go out far enough to the outskirts, they are baryonically close, meaning the fraction of baryons to dark matter is close to that's out in the ambient medium. But we won't go through that. Let's just do BBN because we haven't really touched upon it at all. So I won't be able to go through the physics of BBN, but what I'll try to sketch is essentially what are the observations that are giving you the baryon fraction from BBN. Okay, and so if you want to clarify things, go ahead and ask questions, but we can't go into any details with BBN. Okay, so there's 3 elements that whose abundances we try to constrain, and that's helium-4, deuterium, and lithium-7. To 0th order, BBN is a process where you try to take all of the neutrons and protons and try to create helium. This is the path the path that BBN takes, and deuterium and lithium-7 you want to think of as things left over, things that didn't quite in this process of going from neutrons and protons to helium-4. It's not a complete conversion, so in a sense it's whatever you couldn't burn in this direction. Okay. So the quantities, these things are in much smaller quantities. This is a part in 10 to the 5 compared to hydrogen. This is a part in 10 to the 10 compared to hydrogen. Okay, but you can measure them. For example, these things are measured out at cosmological distances this is measured sort of in highly ionized regions with gas. This one, you try to look at regions that are backlit by quasars, and you try to look for the absorptions. And so it's dominated by regular hydrogen, but the spectra shifts a little bit because the mass of the deuterium is different. So you try to pick out deuterium based on that small isotopic shift. Very, very hard measurement to do. Okay, but this is, by itself, this is the best way to measure the amount of baryons there is in the universe, because the more baryons you put in, the more efficient the process is of converting everything to helium, the less there is of deuterium. So deuterium is very, very, very sensitive to how much baryons you put in. To zeroth order, what the BBN calculations care about are this quantity eta, which is number density of baryons divided by the number density of photons. And if there isn't really any entropy production after BBN, then this quantity is the same as that measured by the CMB. Okay, so we'll see the comparison to the CMB in just a second. Okay. So that's the thing that BBN cares about is number density of baryons to number density of photons. Okay, so I will give you some numbers from a recent review by Gary Steigman. So you can ask, like, in order to get the observed helium abundance, so helium abundance is typically written this way. So this is basically the mass fraction of helium in the universe. And you know this is about 0.25. The measured value is, and again, this is a field where there's a lot of debate about the exact values that go in here. So different people come with different values because the name of the game is systematics, which you don't understand. And so depending on how you do it, how you dissect the data sets, you can get slightly different results. This is sort of Gary Steigman's conservative way of putting some error bars here. So that's what I'm taking. Deuterium over hydrogen. This is even more thorny because formally the statistical errors on these measurements are much smaller than the scatter from measurement to measurement. So again, you have to be careful. In here, the error is sort of like 0.1-ish. Okay, so okay, so that's basically, the universe is mostly hydrogen and helium. There's some little bit of deuterium, and there'll be even less of lithium, which I'll come to in just a second. So you can just ask, like, well, if I want to just explain helium, how many baryons to photons do I need? What do I need for the baryon number of the universe? Okay, and so that's a nice way of looking at consistency. And so here's the numbers from Gary's review. This is, I'll just write this as get helium-4 right. You need a number which is 11.5 plus or minus. The error bar on this is big, and physics-wise that makes perfect sense because lowering or raising baryon number by a little bit doesn't really affect the main process, which is all of these neutrons getting bound up into helium. Okay, so it's not that sensitive. It is, but it's not that sensitive to the baryon number. Okay, and the sense in which this varies with eta is that as you jack up eta, the processes that convert, the nuclear physics processes become more efficient, and you get more helium. Okay, so there's a slight increase in the helium abundance as you change eta. Okay, you can do the same thing for deuterium now, and ask what that is. Okay, get deuterium right, and for that, it turns out the number is 5.96. And look at the error bar now. Okay, they're completely consistent with each other. There's no discrepancy here. Right, this is at 1.5 sigma. They're both completely consistent. But the error bar on the deuterium is very tight because deuterium is very sensitive to eta. As you increase eta, the amount of deuterium you get just drops, right? And that's simply because the processes that it's very easy to destroy deuterium, right? The binding energy is 2 MeV. Doesn't take a lot to destroy it, and so it's very, very sensitive to how many baryons you put into the universe. Okay, so here they're consistent, and so when people tell you that BBN constrains the baryon fraction, essentially what they are really saying is it's the value of deuterium. So deuterium is sort of the thing that actually gives you the baryon number of the universe. Okay. So a good number to adopt is 6 times 10 raised to minus 10. Right? And then as soon as you have that number, you want to ask, well, is this consistent with what we get for the CMB? Okay. So let's convert this to omega b h square. I don't know if I did this here, but so you would write omega baryon h square. And to do this, you would need to like first find the mass density. So you would multiply by sort of the typical nucleon mass times the number density of baryons to give you the energy density of baryons. Okay, and then you want to do this. You want to extrapolate from BBN to today. Okay. So I'll put a subscript there and divide by the critical density. Okay. And you can do this really well in terms of eta, because if there's been no entropy production, this guy is constant, right? And then I know how n gamma scales with temperature. So this becomes in terms of eta, there's a direct relation between omega b h square and eta. Okay. And so let me write that down here. It's eta into 10 raised to 10. And really, there's pretty much no uncertainty here. The only uncertainty is in what you've assumed about the universe. You've really assumed that since BBN, there's been no entropy production, which means that this ratio stays constant. Okay. Okay. So now you have eta, and this relation, like I said, is just dependent on whether there's been entropy production or not. Plug that in, and you will find this is 0.0219. If you take that eta and plug it in. And you guys remember from CMB, it's 0.022. Okay. And that is incredible. It's two completely different measurements, completely different systematics, right? There's nothing common between them. In one case, we're doing nuclear physics at an MeV, measuring stuff which is like deuterium and helium abundance. And in the other case, it's a CMB measurement, last scattering surface, completely different physics. And they give you something that consistent. Okay, so it tells you something is right with what we are doing in terms of cosmology. Okay, right? So that to me is a pretty amazing, consistent result. And now you stare at this and you realize this is 0.02. That's 0.141. So something like a fifth or so of the total matter must be baryons, right? So this is the strongest evidence for non-baryonic form of dark matter. Okay. And when we talk about the CMB, when we say CMB is a measurement of non-baryonic, what we are implicitly saying there is the CMB is measuring the non-baryonic part is the things that don't interact electromagnetically. Okay, and in case of the BBN, that's also true, but we're also talking about nuclear physics, right? So it's a very, very consistent picture. Any questions about this? Okay, so we'll do one more scale, which is from the CMB, and then I'll try to sketch. Neelima may have gone through it, but I'll try to sketch what happens when you change some part of the dark matter to baryons to the CMB. Okay, and it turns out that you can actually basically predict that from very, very simply without doing a lot of work. Okay. But you will have to take something. The first line I'm going to write down. That's something that I won't be able to derive because it'll take probably a good 20 minutes to half an hour to derive that. Okay, so we've sort of looked at this KE scale. We've looked at BBN. Now we're going to the CMB to look at the scales that are relevant there, because CMB by itself gives you omega BH squared and omega matter H squared without reference to anything else, any other experiment. Okay, so and it should be a review. So it's good to, like, if you've seen this once before, that's really good. This is the metric you've now seen multiple times. And I'm just taking the a square out front and writing this d tau, which is a more useful variable to deal with. Sometimes it's called the conformal time, and it's related to the usual coordinate time, like that. Okay, it's just a little easier when you write out the equations in that, but there's nothing more subtle here. Okay, so for the CMB, what we need is we need to talk about the temperature fluctuations in the CMB. I'm going to first write down one equation that I'll try to motivate in a very simple way. And if you want to look through the derivations for this, use Scott's book. Okay, that's one of the two fundamental equations you're going to deal with. Sorry? Oh, you can say I missed the joke.
This phone went off.
Oh. So this, what we're really doing is we are expanding the, and I'm guessing that this is something you guys have seen. So we're basically expanding the temperature fluctuations. Remember that in principle, this depends on where you are, in what direction the photon is. Okay, and so, but again, we don't do things in real space typically, and the reason is for linear physics, if you do the Fourier transform, each mode just propagates on its own, and so we typically look at the Fourier transform, and you should put a twiddle here, but of course, most people will drop that subscript too. Okay, and so you think of it in terms of K and Q. Q is the momentum, the direction you're looking at of the photon. Okay, you can also write it as n, the direction if you want. Probably better to write it as n if it's confusing. And so you can show then that for the CMB, really, that what matters is if you start out with conditions that are isotropic, then the only things that are relevant is the wave vector k. So this thing depends on the wave vector k and this angle. Okay, and then the name of the game is to just expand it out in spherical harmonics. And this is the monopole term. This is the dipole term. So you can think of that as sort of the monopole, the temperature fluctuations, and this is the velocity perturbations, if you want to think of it that way. Okay, but that's what it is. In principle, you have to write down the full hierarchy. In practice, life is much simpler when there's a lot of scattering going on, because scattering essentially tries to isotropize things, and so all you really have is these two things. Okay, so for the largest period of time until the very end of recombination, these are the only two things you would need to care about. Okay, and that was the insight of Celeryaga and Seljack that made them, do this line of sight integral that sped up CMB calculations 100-fold or whatever it was. That is that it is pretty simple. You just need to keep track of a few things. Okay, so this is you can think of this as the continuity equation. One way to motivate this is a little bit of a cheat, but it's actually not so bad, is to think of what the fluctuations in the number density are of photons. Okay, and if you look at this term here, you realize that if you're looking at some small volume in coordinate space dx cubed, then the actual volume is going to be a cube dx cubed times 1 plus 3 phi. Right? Essentially, the 1 plus phi is sort of the perturbation in each direction. Right? So the fluctuations in the number density will come from both the fluctuations in the temperature and the metric fluctuations. Right? So you can write the fluctuation in the number density as the original number density of photons times 3 theta. Okay, and that's just coming from the fact that n goes as t cubed. Right? And then you have 3 phi. Okay, and then just do the usual continuity equation, which is derivative of number in some sphere is equal to the flux of stuff going on. It's the divergence of the velocity, and the divergence gets converted to a k because when you do the Fourier transform, this just becomes right. And this ik dot v is what's typically written as this theta 1 is essentially this quantity. So that's the sense in which you can call it the velocity perturbation or the dipole term. Okay. So this really you can just think about it for a little bit and just realize that's the continuity equation. So the second equation that you have is essentially the equation that it's basically the Navier-Stokes equation. So it tells you about momentum conservation. It's harder to do this kind of a trick with that and try to write everything down because in the end there is radiation here. You got to do GR. But we can write down the second equation very simply. I'll write that down and then that's sort of what we'll need. Okay, so let me write that equation down. And it's going to look tricky, but that's okay. Okay, so there's this term R that has now come in, and R is defined as 3 times rho baryons over 4 times rho gamma. Where does this come from? It comes from the fact that momentum is basically rho plus P, and for baryons it's just rho. For photons it's rho plus 1/3 rho, so it's 4/3. And so this equation is not the equation just for the photons. What's been done here is to realize that the photons and baryons are coupled, and so you got to conserve their momentum together, and that's where this equation comes from. So this R is essentially telling you about, and this is very, very important because this is what is going to tell you about the baryon to dark matter ratio. So this R is essentially telling you about the inertia of the baryon photon fluid. Okay, and there's pretty much nothing tricky about this equation. There's been 2 equations that's been combined. One is the equation for theta 1 dot without worrying about baryons. Then there's another equation for the baryons. Then you realize that the 2 have to be coupled in the way that if the momentum transfer from the baryons to the photons is equal and opposite to the momentum from photons to baryons, then you write them together, and this is what you get. Okay. Again, this one you can sort of see it's V dot. This is the grad phi term, so this is the gravitational force, right? So you remember V dot is going to be any forces on the right hand side. So the forces come from gravity, which is that. Grad phi has gotten converted to a k psi. Anytime you have a grad, do a Fourier transform, you get a k. There's a 1 plus r because the mass matters. This is sort of the analog. It's coming from the gradient of the pressure. Okay. Why is it temperature? Because pressure is essentially the pressure of the photons. Photon pressure is 1/3 rho, so it's essentially just dependent on the temperature. And again, gradient of the pressure, the gradient becomes a k. Okay, and this is sort of the damping that comes from the expansion. So it's if you forgot about that, then it really is what you would have sort of written down, maybe up to factors of order unity. So it's very simple. I mean, I'm not deriving it for you. You can go and look at it. It literally will take you just 20 minutes when you go through Scott's book. But I want you to sit back and just realize that when you think about the physics, it's pretty simple, right? As long as the baryons and photons are really coupled. Okay.
So I know the phi is the fluctuation of temperature. Can you write down the actual equation?
This one? This theta, is that's just that, right? So that's basically the monopole term. So it's delta t over t integrated over all angles, right? And then theta 1 would be delta t over t integrated over p1 cosine theta, or cosine of that angle. Okay, so the beautiful thing you can do now is to combine this equation and that equation, and what you'll see is, so you take this equation, that equation, write down just one second order differential equation for them. And this was done by, for example, Hu and Sugiyama. And I've taken the 1 plus r factors and put it in the denominators. So now all we're doing is combining these two equations and writing down a second order differential equation for theta naught. And this is really all you need. So the right-hand side is going to look complicated, but you don't have to worry so much about it. It's basically something. It's basically something that only depends on the potentials, and so they're all coming from the fact that I'm going to take a derivative here. So theta double dot will give me a phi double dot. Then I get a theta 1 dot. For the theta 1 dot, you go and use this and replace it. And so you get some mess on the right-hand side. But the mess on the right-hand side goes in the following way. This term is essentially sort of a grad square psi. And for most practical purposes, the magnitude of psi and phi are equal. In fact, in the absence of neutrinos, phi is identically equal to minus psi. So you can just think of them all as phi's if you want. This is sort of this, phi double dot. And this is also proportional to phi double dot, essentially. Okay, so on large scales, these guys will dominate. On small scales, the gradients will dominate. Okay, so this is sort of the driving term, and on the left-hand side is a harmonic oscillator. Right. This, and if you write it out like this, this is basically the k square term. So that tells you the frequency of the harmonic oscillator, and this is the damping part. So remember that if you get a x dot in the harmonic oscillator equation, it's a damped harmonic oscillator. So this tells you about the damping, and the damping is coming from the expansion history, the fact that the universe is expanding. Okay, so this equation is why. It's simple physics, why you can really think about these oscillations and everything in very simple terms. Okay, it's a driven, damped harmonic oscillator whose mass is varying. Okay, but still a harmonic oscillator. And the mass is given by this, it depends on this 1 over r term, which if you put it 1 over r here, then you would think of it as a mass term. I've just taken it here because normally we think of this as sort of k square times the sound speed square, where the sound speed square is written as 1 over 3, 1 plus r. So if r was not there, then the sound speed would just be 1 over square root of 3, which is the usual sound speed for radiation. But because of r, it's a little smaller because there are baryons. Okay, so these are the things that give you the nice peaks and troughs in the CMB. As it stands, and those peaks and troughs would continue just like that. But there's one bit of physics missing here. We're not going to do it, but we'll just say it, which is I assumed in doing this that the baryons and photons were completely coupled very well, which is not the case. Towards the end of recombination, as hydrogen atoms form, this coupling breaks down. It's no longer a perfect fluid. Viscosity creeps in. So things get complicated. You can still do things analytically, but what ends up happening is the fluctuations get damped. Okay. Now that process by which this perfect fluid approximation breaks down is very, very important, because remember there's no theta 2 term here, and if there's no theta 2 term, there's no polarization. when this perfect fluid approximation breaks down, you generate a theta 2 and higher moments. But theta 2 is the biggest of those higher moments. And this is what leads to the polarization of the CMB. At this level, there's no polarization in the CMB. So all of the polarization you see in the CMB is produced in that last phase as the universe transitions from being ionized to neutral. Okay. It didn't exist before. Right? So that we won't do. For us right now, to just describe the physics, we need to think about dark matter. This is all we need. Okay. So this is the scale of the oscillations, right? Ks Cs squared. And so those peaks and valleys you see in the CMB is determined by this. And so like K equality, the scale we care about in the CMB is called the sound horizon. And that's just the integral of this sound speed. You can just do this tau last scattering. So it's sort of define the time when the photons last scattered in some probabilistic way. And so the sound horizon is just essentially the distance the sound waves could have traveled in this fluid. Okay. And we know what that is because we've written down Cs. So I'm just going to call this tau star here. And Cs is just that term. It's 1 over square root of 3, 1 over square root of r, but r is 3 rho baryons over 4 rho gamma and integrated over the time. And remember, you can exchange time for a scale factor if you want, and we'll do that right now. The other thing to notice is that baryons are going as a to the minus 3, photons are going as a to the minus 4, so this ratio here is going as a. So I can write this down as 1 plus 3/4 omega b over omega gamma, because that's the densities today, but just multiplied by a. And instead of dealing with tau, I can just deal with a over. And this just comes from the expansion history, right? So a dot over a square is just h naught square root of omega matter right? And if you pull the omega matter out, you can write this as omega matter h naught square square root of a to the minus 3 plus a to the minus 4 times a equality. So again, a equality is in, omega matter is in, and this is how you're going to get omega matter out of this and omega baryons. Okay, so that's an analytic integral. You can solve it. Since it's such an important one, I will write down the answer. It's also one of the problems in Scott's book, chapter 8. So it's just do that integral. It's analytic. So this R eq is just, so R is basically, as we wrote down there, 3 or 4 omega b omega gamma, not the radiation, just the photons, times a. And so R eq is just the value of R at a eq, at a equality, right? And so you can see again the same scale k eq is in there, but you get this R eq, which now depends on omega b. Okay, so now it's very simple to actually analyze what's going to happen to the CMB. We can easily make a prediction. Okay, and let's instead of me doing it, let me just give you this problem, which is if I take omega matter h square, right, and this is normally written as omega dark matter h square plus we don't need the h, omega baryons. and I convert some of the dark matter to baryons, but I keep the total matter fixed. So I'm not changing the total matter. I just take some fraction of the dark matter and turn it into baryons. What's going to happen to the peaks in the CMB? Is it going to shift to larger L, which is smaller scales, or smaller L, which is larger scales?
Turning up DM or turning down?
Turning down DM, and so more baryons, less dark matter. So I'm going to do take something away from it and put it into baryons. So more baryons, less dark matter, but keep the total fixed.
You shift to a lower L.
Shift to lower L. Why? So what's happening to RS if, sorry? It's smaller because this guy is fixed. That guy is getting a little bigger. So RS is smaller. But if RS is smaller, which way do the peaks shift? To the right. So you were saying the right thing, but you were interpreting it wrong in the L. Yeah, so it does go to smaller scales. And so the easy thing to do is, and you can just do this if you want to go and like on the NASA websites, there's a web version of CAM. If you want to plot it out, you can do it. So one quick thing you realize is the peak positions are very sensitive to it. But that is not the way you would typically just be able to pick. There are other things that can change the peak position. So there's got to be more to it. And it's something I think Nilima talked about. What else happens here when I increase baryons but keeping the matter density fixed? Yeah, and where do you guys think that comes from? It's again going back to this harmonic oscillator, and this was the first time I heard about this from Wayne, talks, and he explained this in a very nice way in thinking about harmonic oscillators. And if you have a harmonic oscillator and you have more mass, then the equilibrium shifts down, right? And so the first peak, which is the compression peak, really goes up, whereas the second one, which is the rarefaction, gets suppressed. And so the ratio of the first to the second peaks, it just depends really. It's very sensitive to this R. And R, remember, is omega B over omega gamma. And the experiment we are just doing is keep the dark matter fixed, but keep the total matter fixed, turn some of the dark matter into baryons. Okay. So I can now plot this very easily. I should have brought a picture, but just as much fun to plot it. So if I take a normal, and I'm going to do a linear scale because I don't care about the large scale features here. Okay, 7 peaks or so. Amazing. Every time I look at this, like even now, I get like goosebumps. Like just to imagine that, the same peaks being seen again and again and again. It's completely incredible. Okay, so what we just said that things are going to move to the right. So this is our starting point. Now we're going to turn some of the dark matter into baryons, and you can sort of predict this now. So first of all, we said the peaks are going to move to the right. We also said this will get jacked up. Something like that. And then eventually, I'm doing a bad job here. So all the peaks will move to the right. Okay, like that. And at the end, if you want to know whether this peak is bigger than that peak, that becomes a harder job, because anytime you've gone beyond like the third peak and beyond, this equation is no longer a good approximation. You can't play with this equation because damping becomes important. Okay, and so then the solutions you get are not just that theta naught, but the solutions you get are damped, so they'll get multiplied by. In K space, they look something like this, where this lambda d is the damping length. Without doing anything, just thinking about the process of damping, you can write down the functional dependence for this. We won't go through the physics, but I think it's useful to see it once, or if you have seen it once, see it again. You think of this as a random walk, and you remember that in a random walk, the distance you would travel goes as square root of n steps you take, times the length of each step. Right? And so lambda d should go as something like this. The length of each step is just the mean free path of the photon. Okay? So I can replace this with, keep this square root of n here. This is the mean free path. And the number of steps is essentially the time you have divided by the mean free path. The time or the distance is the same thing. You multiplied by c. So c is 1 here. Right? And so this lambda d is sort of a geometric mean of the mean free path and this tau, which is the time at last scattering. Okay? And tau at last scattering is going to, again, sort of like in the CS, is going to depend on A equality. And the mean free path of the photons, the dominant process is just Thomson scattering. So the mean free path of the photons is just 1 over number density free electrons, Thomson scattering cross section. And since everything is in co-moving units, I'm going to divide it by an A, just to get everything co-moving. Okay, this tau is co-moving, that has to be co-moving, so everything is co-moving. This k is co-moving, which is to say that we're taking a Fourier transform with respect to x, which are the coordinates and not the physical distances. So everything is in co-moving units. So that's basically it. This times that, and there's some factors that you got to spend 4 or 5 pages to work out. But if you forget about those order 1 factors, that's essentially it. So you can then try to figure out in detail what happens here. It gets a little more complicated because the way you really should be analyzing this is to ask at what k contributes to which peak, and then ask whether this peak is damped compared to that peak by how much. You can do it, but it's probably going to take another 20 minutes, and I don't want to. Okay. So it's very, very nice in the sense that, once you go through the derivation, takes you a couple of hours to maybe go through the entire thing properly. You can step back and think of this as just a harmonic oscillator, and all of the physics that's leading to you, for leading to this inference of non-baryonic dark matter is very simple, and that's why you want to trust it. Okay, this is just the temperature. You can also do the polarization. We don't have to do any physics. We can just plot this without doing much. And so this would be L square CL, for example, the E mode polarization. And typically it looks 1, 2, 3, 4, 5, 6. And that's somewhere around L of 1,000. Okay. The same thing is going to happen with this, which is that the peaks are going to get shifted to the right. But in this case, the intensity is going to drop, and that is related to R. It's related to this theta too, because this guy is directly proportional to that guy square. I'll leave it to you to figure out why it drops, but the shift is the same. Okay, when you change some of the dark matter to baryon. So we have independent handles in the polarization and the temperature. Okay, questions. So we've basically gone through now pretty much every single piece of evidence, major piece of evidence in astrophysics and cosmology for dark matter. Any questions about this? Okay. So I want to spend the next 15-20 minutes just thinking about all of this was just basically thinking about evidence for dark matter, but we haven't really talked much about can we go beyond this and talk about the particle nature of dark matter. So let's do a couple of quick examples so you get to see how you would do those calculations. L of 1,000. Why is there the weighting? Because it's not the same thing, because it doesn't come from theta 1 and theta 0. It comes from this theta 2. And so when you write out this L square CL, the structure is different. Yeah. Yeah. Do we still have that figure there?
Yeah, you have the.
Oh, it's. Okay, yeah. So this picture was, thinking about the harmonic oscillator, and so when you increase R, remember in that harmonic oscillator, R is playing the role of the mass, right? And so what it's doing is basically, if it's a harmonic oscillator here, and you add more mass, it shifts this equilibrium position, right? And so the first peak is the compression peak, and so that is, so imagine you start out with some amplitude. And so that you've just increased that, and the second one is the rarefaction, and you decrease that. So that's essentially what it is. And it literally will take you like 20-25 minutes to write out the solution to that, and you will see it. Just jack it up, and you'll see exactly that happening. It just gets very tricky out here because of the damping, but otherwise here it's very simple. Okay. So this one we won't be able to do any real equations for what I'm going to tell you, but what I want to do is to give you a sense, like, if you're thinking about different kinds of hidden sectors, what are the processes in the early universe you need to worry about, okay? And they fall under the basically two simple categories. So the normal thing when you think about dark matter is chemical decoupling. So I'm going to have time run like this. Right, and you guys talked about this a lot, about the production of dark matter. Neil wrote down the equations for it, so you've seen it more than once. But once the density of dark matter is set, it can still scatter off of other light particles in the hidden sector, or other light particles, or the fermions in the visible sector. And so there's a phase in which the dark matter is kinetically coupled to light stuff. And this is very crucial, because when the dark matter is coupled in this way, the equations, and that's why I wrote down those equations. The equations are basically the same as this. Just replace baryons by dark matter and theta by whatever light fermions there is, and this is exactly the same equation you're going to get. Okay, no different. There's a sound horizon. It's just that these things are happening at early times, so the sound horizon is going to be much smaller. But it's identical physics in terms of what ends up happening. Right? And so examples here. Let me set this up. So as a simple example, like, then what you really want to do is figure out when it is that the dark matter decouples. And to do that, you need to do your usual thing, which is find some gamma for this scattering processes and equate that to the expansion rate. And then you find when it decouples. And so what's relevant here is the same calculation we did for the relaxation time with gravity, which is how many scatterings does it take to change the kinetic energy of dark matter by order 1, and how long does that process take? Okay. So I will write this out as, so this would be, in any given process you have, that would be for one single collision, what is the average change in the kinetic energy over the typical kinetic energy of dark matter particles. And then there's some degrees of freedom that you're scattering off of, and they should be light. So its number density goes as T cubed, and this could be the visible sector if everything is coupled properly. Or if you're thinking about hidden sectors, this could be the hidden sector temperature, which could be different. So you need to like plug that in properly. Okay, and then there's a cross section for this process to happen. Okay, so this bit now thinking dark matter interacting with some light fermions. This process. Okay, and there's no velocity because we're assuming it's light fermions. So it's basically c. Okay. So that's the typical scattering rate. And so any given process you have, you can just compute that and set that equal to h as a function of t. Right? And these two t's, just remember that might be different. I mean, this could be the hidden sector temperature, so then you need to take that into account. Okay. Yeah, so this is basically so that it is a diffusion process, so it's playing the same role. So it's just how many scatterings do you need to change the kinetic energy by order 1. So now it's diffusion in energy. Before we were thinking about like diffusion in actual real space. So it's exactly the same. Yeah. Yes. So the number changing guys are done here, all right? And so that typically decouples early. Now we're thinking about this process where all you're doing is exchanging energy. Right? And so in this time here, when the dark matter is kinetically coupled, its temperature is actually, the temperature of the dark matter is basically the same as the temperature of the light fermions, which is typically scaling as 1 over A if there's no entropy production. Okay? It could. Yeah, this is happening before also. Yes. Yeah. But for typical parameters, this thing freezes out much later than the the parameters that change, like the dark matter annihilation processes. That's true. Yeah. Anyway, so in this phase here, this is what's happening, and so there's some temperature where this, which we can call decoupling, where this is satisfied, and after that, so this after decoupling. The temperature of the dark matter, how does it go in terms of scale factor? Right? And that's because velocities are going as, once it's decoupled, the only thing that's happening is the momenta are just diluting away as 1 over A. And if it's non-relativistic here, I'm implicitly assuming it is, the way I've set it up. So the temperature is just p square over m, and so the temperature will drop as 1 over a square. But velocity is dropping as 1 over a here, and here the effective temperature is coupled to that of the light degrees of freedom, so the temperature of the dark matter is dropping as 1 over a. Right? So this is the setup. Most models you would write down will fall into this category. Doesn't matter whether it's a WIMP or some random hidden sector model you write down. There'll be something like this going on. Okay, why is this decoupling important? Because once you compute this to order unity, you can immediately tell what happens in the late universe. Okay, and that is there's some length scale lambda d, and this is why I did the whole CMB stuff. Lambda d is the diffusion length. Okay, so remember in the CMB, as the hydrogen atoms were, as the universe was going neutral, the photons could travel further and further out. It became a diffusive fluid. You get a diffusion length that's large, and so there was a diffusion length that damped everything. The same process is happening here. As this process starts freezing out, the dark matter can go diffuse out further and further. So there's an effective diffusion length for dark matter. And that's again said by that same random walk argument that we had. Right? And in this case, it basically turns out to be something like the time at which this decoupling happens, which you can compute very easily because you know that this is just dependent on the expansion history. You know the radiation density. So again, taking into account hidden sector temperature, visible sector temperature differences, this is pretty simple to calculate. And then this is let me just write this down. You can ask like what is the mass enclosed within this length scale? So that would be 4 pi over 3 density of dark matter times this lambda d cube. And the way I've written it, it's the density of dark matter today because everything is in co-moving units. And typically, that is the size of the smallest halos in the universe. Okay. It's pretty simple to calculate. So there's some order unity factors that are not right here. There was a recent paper titled Ethos by a bunch of people. They did numerical simulations and they have a better formula. So in the end I was going to look this up, but I forgot. But their formula looks like this: M minimum or M cut is some number times T decoupling cube. And the reason it's T decoupling cube is just coming from the size of the universe at that time. Okay. And so this, as soon as you compute this for any given model, you know the minimum halo mass in the universe up to factors of order unity. So I'm sorry I forgot to get this number, but you can look it up in the Ethos paper. I'll put it in my notes. Okay. So it's very cool. You don't really have to work very hard now, right? That one is, if you can write down a Lagrangian, you can write down the cross section and do this calculation, and you can get the minimum halo mass. So for WIMPs, if you calculate this, it will turn out that this minimum mass is somewhere around an Earth mass. Could be larger, could be up to the mass of the sun, but it's somewhere in that ballpark. Right? But for typical models, this decoupling could happen much later. If the decoupling happens around a keV scale, then you're going to get this minimum mass is going to be very large. It's going to be like 10 to the 9, 10 to the 10 solar masses, things you can observe. So depending on what sort of models you have, this can be either observable or like WIMPs, it could be very, very small. Okay. This typically is in these kinds of models where you have some coupling to light particles. This is what sets the minimum mass scale. Okay, so you need one more thing, and then that's it. The other thing which we haven't talked about at all is, okay, so it decouples at this point, and it's free streaming away. But we know something else happens when you free stream, which is just this process of free streaming can wipe out fluctuations, right? And that one's something you're more used to because you've seen the free streaming scale written out. There's a nice paper by Avi Loeb and Matthias Zaldarriaga where they derive this from a simple Boltzmann equation, and you have to all love Boltzmann equations, so that's the real derivation sort of to look at. But we can also like hand wave this and just do the free streaming length is just decoupling to equality I'll write this down in the proper form first. V dt over A. And if you go to Kolb-Turner or any typical way of calculating this is what would be done, which is the free streaming scale is after you decouple, how far do you travel? And again, this A is to make everything co-moving. So in a small period of time dt, you travel V times dt, and then divide by A to make it co-moving. This depends on the scenario you start out with, but for these kinds of scenarios, from decoupling to T equality, it's pretty simple to calculate. Now, this velocity is not a unique thing, so you should normally average this over the distribution function. Right? But it's not hard to do. When you do it, let me just write out for this. Again, it's the sort of WIMP-like scenario. Here's the numbers you get. And more than just the functional form, I'm writing this down to like point your attention to what the mass scales here are. So this log term I'm writing down there, it gives you some order unity things. So T decoupling is when the decoupling happened. A decoupling is the scale factor at that time. T nu 0 is the temperature of neutrinos today. I've normalized everything to that. And then for the mass, I just took a keV just to give you a sense. And so if there was a WIMP-like thing with a keV mass, it would have a free streaming scale which was 0.2 megaparsec. That is big. And the Lyman alpha would be very constraining at that point, because you would see this cutoff in the linear power, in sort of the Lyman alpha power spectrum. Yeah. Yeah. Yeah.
That is basically by the radical.
This is your usual dark matter density. Yes.
This mechanism tapping of the circuit of dark matter basically has the same physics as the.
Absolutely.
Then you're saying this looks like different types of moments.
Yes.
Then, I thought that there are more mechanisms
This is collisional damping in it, because it is collisions of the fermions, right? It's if the fermions are essentially massless, then it boils down to the same process of silk damping that was going on with the CMB. And the second process I'm saying is this. So maybe I'll draw you a figure right now, and that should sort of summarize the whole thing. But before I draw that, I just wanted to say that, if this was a typical WIMP, you're going to put 100 GeV here, right? And this is going to be unobservably small, right? So if you put 100 GeV out here, kmg, so that's 8 orders of magnitude, right? And so this would become something like parsec scale, right?
Length scale of the first streaming of the dark matter, right?
Exactly.
Then I think of that there's a history below this length scale.
Yes. So whichever one dominates, it could either be this process, so this diffusion length that dominates, or it could be this. So whichever one dominates is important. So let me draw. So really what we are now saying is, if you look at the power spectrum of dark matter, right, you guys did the whole, it looks like that scale, right? But let me just divide it out by, so look at the power spectrum, but divided it out by a power spectrum where the decoupling happens very early. So take T decoupling to infinity or something. Okay, so this is just saying that the decoupling happens very early. For all practical purposes, the particle is very, very, very cold, so I don't have to worry about it. So, but now when you crank up T decoupling, what can happen? On large scales, nothing. This is the acoustic oscillations from this decoupling phase, right? It's the same physics that's setting the CMB fluctuations. It's the same thing that you see as baryon acoustic oscillations in the baryons. This is the dark acoustic oscillations. It'll happen unless you write down a model like sterile neutrinos that are born non-relativistic. In most other models you're going to write down, WIMP-like models, it'll have this feature. It's just a question of where that scale is. This envelope here, that's the free streaming. Right, so it basically, you can get situations where the free streaming is more important or the damping is. I don't have a good answer for why it goes that way, but most of the models, it's this damping process that controls it's this first drop here that's most important. That sets the minimum size, so it's this one. But for a sterile neutrino where you don't have that process, then you would compute the the free streaming scale, and that would set the minimum mass, right? And that's sort of we did. Right? So it's exactly the same physics mirrored in the CMB. That's in the CMB. In the CMB, it happens on 100 megaparsec scales. Here, it can happen anywhere from below a parsec to 100 megaparsec. You have this huge range. Okay, and so mostly what I wanted to get across to you is that you don't have to be scared of doing a whole lot of technical stuff in the early universe. If you have a model you're working on and you want to take a first blush shot at like what it's predicting for the early universe, things are pretty simple. You can just estimate these parameters, right? And you don't have to work that hard for it, and sort of get a sense for like what's happening to the power spectrum. Right? So that is, and as I said, the physics is basically the same as in the CMB. So this is just the same stuff here. So it's when you just work it out, you're going to get you remember that when you do the free streaming scale, you get a log when you do the integral. So that this is basically just that log. It's 900 mass in a keV, temperature of the neutrinos today divided by T decoupling, A decoupling. So it's just that stuff going in there. So this is going to give you some number, maybe like few. And I just put the M as a keV just to tell you that for a keV mass, you just get a very large free streaming scale, which is warm dark matter like. Yes? Why did we set that is there is isn't a very good rigorous answer for that. So I don't know where it is. Oh, here. It's just mostly because you can extend it beyond TE, and the contribution you get from there is very small. So it doesn't really matter. It's sort of like in the same sense in which we do Coulomb logarithms. There's a log factor here, so that will just go into the log factors, and it doesn't matter so much. Okay. Yeah. So it's just a very convenient place to stop. But if you did go like 5 times T equals something like that, the answer wouldn't change much. Because, yes, and more importantly, before T eq, T goes as a to the minus 2, and then after T eq, if it's not a sudden transition, this is going as a to the minus 3/2. And I won't get it right, but if you do the integral, then you'll realize that after T eq, the contribution to the integral is very small. So you just stop at T eq. Do it. But in any case, you should stop well before nonlinear structure formation happens for that scale, because at that point, this whole stuff is totally wrong. Okay.
Is there any case where the envelope comes up before, in a smaller scale than the exponential that sets the...
Maybe there is, I don't know. I haven't seen a model like that, but maybe there is. You can play around with it. Maybe it's, a good place to look at is like Francis Janssen-Racine's papers, where they do these dark acoustic oscillations. So they go through some different examples there. But the things I've looked at are more WIMP-like stuff, so almost all the cases had like 10 parsec scale. And in those cases, these oscillations were the ones that ended up setting the minimum mass, and not the free streaming scale. Anything else? Okay, I was going to spend 5 minutes summarizing everything we did with slides, but we ran out of time, so maybe that's a good thing. So if you don't have any more questions, then we can break. And thanks a lot for your attention, questions.